Okay, welcome back. So we're going to be starting section 3.4 today, which will be concavity. But before we do that, let's knock the homework out from the section 3.3. So we'll start off with number 24. Each of these is very long, but that's okay. We'll get through it. So f of x was equal to x cubed minus 6x squared plus 15. Alrighty. So first thing we want to do, are there any critical values here? Critical values, any discontinuities? There are no discontinuities whatsoever. So it's a nice polynomial. We can move on to the second part. And so the second part was find the critical numbers, right? So what are the critical numbers? Well, first thing we need is to take the derivative. So f prime of x is going to equal 3x squared minus 12x. Okay? So first part of finding the critical numbers are there any discontinuities? I guess we got to do part A or whatever. It doesn't really matter. There are no discontinuities because, again, this is a polynomial, so we're good there. Now, second part of finding the critical numbers is where f prime of x equals 0. Well, that's going to imply that 3x squared minus 12x equals 0. Now I'm going to swing that over here to be able to continue it. So 3x squared minus 12x equals 0. I can factor out 3x. So 3x times x minus 4 equals 0. X equals 0 and x equals 4. Okay? So those are going to be my two critical numbers. What are the critical numbers when it's saying that f prime of x equals 0? What are those that we just found? Well, these are where we have our mins and maxes. These are places where we have horizontal slope. Alrighty. And in our case so far, it's just been where we had mins and maxes. So that was the next step, was finding the critical numbers. Now that we found the critical numbers at x equals 0 and x equals 4, we need to make the table. So I'm going to clear this and make the table. So step 3, if you will, we'll make a table. And I know that I've got the numbers a little bit off sequence because I want us to start doing, for the very first step, discontinuities. Discontinuities tell us a lot. It tells us where we have our vertical asymptotes and gives a lot of behavior for the graph. So that's why everything is kind of shifting forward by one. So we're going to make the table, and this is the table for the critical numbers we found where f prime of x equals 0. So we had two values to look at. We had x equals 0 and x equals 4. Okay, so for those two critical numbers, I need to do test values on either side. So give me a value less than 0. I agree. X equals -1 sounds perfectly fine. And as always, I'm going to plug that into f prime because I want to know the behavior of the slope to either side of the horizontal slopes. Is it going up? Is it going down? What's going on? So f prime of -1, well, I need my f prime function, so f prime of x was equal to 3x squared minus 12x. Okay, so I'll plug a -1 in. This is going to become a +1 when I square it, so 3 times +1 is 3, minus 12 times -1. Minus times a minus is a positive, so this becomes a positive, plus a positive, which is a positive. And that means that the behavior is going to be going up. We're going to have a slope that is going up right there. Okay, next thing, I need a value between 0 and 4. How about x equals +1? Alrighty, we use the same logic over here. This has become a +1 times 3 is +3, but now I'm going to be doing minus 12 times +1. So this is going to be 3 minus 12, which is negative. So negative, which means I'm going to have a behavior where the slope is going down in this interval. And finally, I'm going to need a test value greater than 4. How about x equals 10? If I do f of 10, what do I get? Well, I get 300 minus 120. That is positive, equals positive, so it's heading up. Behavior for that interval is a positive slope. So what does that make x equals 0 and x equals 4? Well, it's going up then down, so that makes this a max, and it's going down then up, and it makes this a min. So look at all the information we just found out. Now I can use these critical numbers. I want to find out where this max and min are located in y space, so I need to find out where those values are located on the graph. So I take my two values and I plug them into the original function. These are the f values. My goodness, losing my brain. These are the y values, and I get y by plugging an x into my original function, f of x. So my f of x was equal to x cubed minus 6x squared plus 15. Alrighty, so first off, I'm going to plug in f of 0 for the very first, where we have a max. Well, it's going to be 0, 0, plus 15, 15. So this point is going to be located at x equals 0, y equals 15. Okay, now I'll plug in the next critical number. This is supposed to be a min, so f of 4. Well, f of 4 is going to be 4 cubed, which is 64. I think that's right, yeah. 64, so this is going to be positive 64, and then minus 6 times 16 plus 15. So this is going to give me 79 when I add 64 and 15, and then this is subtracting. This is going to be 96, so 79 minus 96 is going to be negative 17. So this point is going to be located at 4, negative 17. Okay, so I have everything I need to sketch the graph. Let me clear this and we will sketch it. So let me draw. It's going to be slightly like not in scale because I really don't want to draw 11 or 15 rather up and 17 down. So I'm just going to put a 15 there and a negative 17 right there. Alrighty, so at x equals 0, we had our max value at y equals 15, and at x equals 4, we had our minimum value at y equals negative 17. So this one is 0, 15, and this one is 4, negative 17. So what does it look like? Well, I also know that I had it going up, then down, then up, so I'm just going to make a curve of some sort. Maybe something looks like that. That is close enough. I can see exactly what the overall shape of the graph looks like, its behavior, everything's good. I could figure out this value where it actually crosses the x-axis if I wanted to. How would I do that? Well, when it crosses the x-axis, what is y equal to? 0. So if I set my f of x equal to 0, I'm going to get something like 0 equals x cubed minus 6x squared plus 15, and then I would solve for x, and I would find the 3 locations where the graph actually crosses the x-axis. Do I want to do that though right now? No, I don't. I really don't. I don't enjoy solving cubics as a rule. So we're just going to leave that and say it crosses somewhere around here and over here and over here. And if I really wanted to know, I could figure it out, but I don't want to know that badly. Alrighty, so now let's move on to the next homework. Clear this. Okay, so the next one was 31, I believe. And for 31, we had f of x equals x plus 2 quantity to the 2/3 power. And this is going to be much more interesting than a polynomial. So I'm going to go ahead and rewrite this into the form that I can understand, which is the root form. So this is going to be the cube root of x plus 2 quantity squared. Alrighty? So I now need to find, are there, first of all, any discontinuities for this? And the answer, no. Since I am both squaring this to where this will always be positive and taking the cube root, which doesn't care if it's positive or negative, And I guess on top of all of that, this is not in a denominator that so I have to worry about the denominator going to 0. So all this says there are none. None for the original function. So now I'm going to move down to my critical numbers. So the critical numbers, well, I have to find the derivative of the function first. So f prime of x is going to equal 2/3 times x plus 2 to the 2/3 minus 1, negative 1/3 power. And then since this is not plain old x, I have to multiply by the derivative of the interior, but that's just a 1 in this case. So we're good to go with just this 2/3 x plus 2 to the negative 1/3. Now I'm going to rewrite this in root notation. This is going to give me 2 over 3 times the cube root of x plus 2. Okay? Now, first type of critical number, maybe an A, I don't know, I'm just making this up as I go along. That's where I have discontinuities. So I need to look for discontinuities. Are there any possible discontinuities with this? Well, there are no imaginary numbers since this is a cube root, doesn't care if it's positive or negative. But it is in the denominator now. So I need to worry about when this is 0. So how do you find discontinuities? Well, if it's not an imaginary, where you have a root of a negative number, it's always where you have the denominator going to 0. So set the denominator equal to 0 and solve, and that will give you where you have the discontinuity. So in this case, I've got 3 times the cube root of x plus 2 equals 0. Now I'm going to divide both sides by 3, which is going to get rid of that. Then I'm going to cube both sides, and when I cube both sides, I'm going to be left with x plus 2 equals 0, or x equals negative 2. So negative 2 is a critical number. So here we go. $10 question, drum roll. What is negative 2? X equals negative 2. What does it look like on the graph? Well, since we had no discontinuities with f of x, but we did have a discontinuity with f prime of x, that means x minus 2 is a, what is it? Yes, it is a cusp. So it's going to be a sharp corner on our graph that is not differentiable. Alrighty, nice. Now let's clear the screen and move on to part B. So part B is where I look for f prime of x equal to 0. So f prime of x equal to 0, I'm going to take, this is my f prime of x right here. Oh, I think I just cut some of that off. Let me rewrite that. Try that again. F prime of x was, let's see, I'm going to write it into the root notation that I did. So 2 over 3 on the cube root of x plus 2. So f prime of x equals 0 when the denominator equals to 0. So I set the denominator equal to 0, and what values of x does 2 equal 0? None. It never equals 0. So there are no locations where I have a horizontal slope. Kind of cool. I don't know if we've done one of these before. So now that I've done that, I can move down into my table. So I need to make my table. I don't necessarily have to, since I only have that one cusp. I could figure out pretty easily what it did, but this is one of the easiest ways to figure out what's going on either side. Just figure out what the slope is doing. So I'm going to take my x equals negative 2 cusp. I'm going to do a value that is less than and greater than that, and then plug it into my f prime. So give me a value less than negative 2, maybe x equals negative, I'm putting 4 here for absolutely no reason, and then I'm feeding that into my f prime. So when I feed negative 4 in, I'm going to get negative 4 plus 2. That is a negative value. Cube root of a negative value is negative. 3 times a negative value is negative. So I'm going to wind up with, for this one, a positive 2 over some negative value, which is going to be a negative, which is what this is going to be. So that means my slope is going down. Okay? Now on the other side of -2, test value, maybe x equals 0. No real reason, pulled it out of a hat. So I'm going to get 0 plus 2, that's positive. Cube root of positive is positive. 3 times a positive is positive. 2 is positive, so positive divided by positive, well, that is positive. So f prime at 0 is positive, which means it's going up. So the behavior of the cusp is it's going down, then up, which means we're going to get some sort of V shape right there. Okay? Now, I can do a quick graph of this. So if I wanted to, no, actually, I don't want to do a graph yet. First thing I want to do is find where this cusp is located. So let's get the y value for that cusp. So I get the y value by taking this x and plugging it into the original equation. And the original equation, let me put that over here, was f of x equals cube root of x plus 2 quantity squared. All right, so now, y value. What does f of -2 give us? Well, -2 plus 2 is 0. 0 squared is 0. Cube root of 0 is 0. So that's at 0. So I get a cusp at -2, 0. All right, final thing. Let's sketch this thing. So kill this, or clear it rather. And then I'm going to have something that looks like x equals -2. And at 2, 0. So this location right here, I have a cusp. The graph is going down, then up based on my chart that I did. So it looks something like this probably. And again, if I really wanted to find out, I could figure out where this is crossing the y-axis, and that would probably give me an idea of what the symmetry looks like. But this is good enough. I know that I've got a cusp down here at -2, 0, and my function behaves like that. So that is totally fine, good enough for me, and I think that's good enough for this homework. So let's move to the next one. Clear the screen, and let's get to it. Okay, so I think that one was 38. And for 38, we had f of x equals, we're going to have x squared minus 2x plus 1, all of that over x plus 1. So first things first, are there any discontinuities with the original function? And absolutely. We have a rational expression here. I set the denominator equal to 0 and solve, and there is a discontinuity at x equals -1. Now, what kind of discontinuity do we have? Well, we have, if I plug -1 in, the bottom goes to 0, the top goes to 1, plus 2, plus 1 is 4. So the bottom does not, rather the top does not go to 0. So bottom goes to 0, top doesn't. That's a vertical asymptote, right at x equals -1. And that's going to help us a lot when we graph this. So next thing we want to do is find the critical numbers. And what do we need for the critical numbers? Well, we need f prime of x. And f prime of x is not going to be quite as easy since it is a quotient. So we're going to use the quotient rule. So if I try that, I'm going to get f prime of x equals bottom x plus 1 times derivative of the top, 2x minus 2 minus top, x squared minus 2x plus 1 times derivative of the bottom, 1. Alrighty? Put all of that over the bottom squared. Okay, so now I'm going to distribute this stuff. So when I distribute x plus 1 through 2x minus 2, I get f prime of x equals 2x squared minus 2x plus 2x minus 2. Okay, and now I'm just going to subtract off this function. It's being multiplied by 1, so it's the same. So minus x squared plus 2x minus 1. And all of that is going to be over x plus 1 quantity squared. Okay? So last but not least, I wind up with f prime of x equal to, alrighty, 2x squared minus x squared is x squared. Negative 2x plus 2x cancel. Plus 2x is what's left over here, so plus 2x. And then minus 2 minus 1 is a minus 3. And all of that is over x plus 1 quantity squared. So that is our f prime of x. So now we can move into discontinuities and all that good stuff. So here we go. So f prime of x, I'll put that over here, f prime of x wound up equaling, it was x squared plus 2x minus 3, and all that was over x plus 1 quantity squared. Oops, I'm not going to do that literally, I'm going to just put the little square right there. Alrighty, so that's what we had, and so the first thing for finding critical numbers are, are there any discontinuities in this? Well, yeah, there's a discontinuity at x equals negative 1, which is totally not surprising because the original function was not defined at x equals 1, therefore the slope is not defined at x equals negative 1. It just makes sense, right? So there are no additional discontinuities right here. We already know that there's a vertical asymptote, so we can move on from there. So next part is where f prime of x equals 0. How do we do that? Well, we set the top equal to 0. So x squared plus 2x minus 3 equals 0. What do you know? We can factor this. That's kind of nice. So we're going to get x plus 3 times x minus 1. So that means x equals negative 3 and x equals 1. Those are where we're going to have f prime of x equals 0. Okay? So these are our two critical numbers that we need to look at. So I can now move to the next step, and that's where we make the table. So step 3, make the table. So I'm going to get, let's see, I'll put the table right here. X equals negative 3, and x equals positive 1. Okay, I need a value to test with my slope up here, this function, f prime, that is less than negative 3. How about negative 4? I agree, that's a nice number. So here we go. Any value I put in for x in the bottom is going to get squared. So the bottom is always positive. So what happens up top? Well, when I square the negative 4, I get positive 16 minus 8 minus 3 is still positive. Positive over positive means that f prime of negative 4 is positive. So I have a slope going up. That's the behavior for this interval. Alrighty? Now I'll move to the next interval, a value between negative 3 and 1. Please say that you pick 0 for that. 0 is by far the easiest when you have stuff like that. So again, the bottom is always positive no matter what I put in it. The top becomes 0 plus 0 minus 3. So f prime of 0 is negative, which means the behavior is going down. Okay, now a value greater than 1. How about x equals 2? So f prime of 2 is going to be, well, positive 4 plus 8, or 4 plus 2 rather. One more time. 4 plus 4 is 8, minus 3 is positive. So this one is positive. So it is going up. So what do we have at x equals negative 3? Up then down means this is a max. And then x equals 1, we have down then up, which means this is a min. Okay? So now I need the y values and sketch graph. I'm going to clear it for this. So clear this. So now I need my y values. And I get that with the original function, plugging into that. So my original function was f of x is equal to x squared minus 2x plus 1 over x minus, or x plus 1 rather. So that's my original one. I now need to see what I get when I plug in my two critical numbers. So f of negative 3 was one of them. So f of negative 3, well, what am I going to get? Oh, I'm going to get 9 plus 6 plus 1 over negative 2. So it's going to give me 16 over -2, -8, which means I'm going to have that point at -3 and -3 and -8. Ooh, I had a total moment there. I was multitasking with my brain and I apparently hit empty on one of the tasks. So ooh, that was weird. Here we go. So that point is -3, -8. Now I'll plug in my next one, which was at +1. So when I plug in 1, I'm going to get 1 minus 2 plus 1 is 0 over 2. So that's just a 0. So the point is at 1, 0. Okay? So here's what I have. This is going to be very, very strange looking. I've got a graph. You saw nothing. I haven't even started drawing yet, so it's all good. So here we try let's go. I have a graph, okay, something like that. And let's see, I'm going to go down to -8. So if you will, I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, somewhere like that. I think I may have cut off a little bit. That's okay. And then up to the top, I don't have to go as far. So 1, 2, 3, 4 is good enough. And then 2, 3, 4, 1, 2, 3, 4. That's totally fine. So I've got, if you remember, the point at -3, -8 was a max. So -3, well, this is strange. Huh. That's supposed to be a max. So if I put a point there, I'm going to have a little trouble. So let me rescale this just a little bit. I'm going to say, when I redraw it, that this is -8 right here. Alrighty? So -3, -8, I've got a dot. That's supposed to be a max of some sort. Kind of odd. -3, -8. And then at 1, 0, so right here, I've got a min. Okay? So at 1, 0, I have a min. Now, how do I go from a max to a min when the max is lower than the min is? Answer. I'm waiting. Give me a second to think about it. Yes, exactly. If you saw it. We forgot one critical bit of information about our graph, which makes this all go away and become very simple. And that is we have a vertical asymptote at x equals -1. So I have a vertical asymptote right here at x equals -1. Now it makes complete and total sense on how to graph this thing. If I didn't have that vertical asymptote, I would be in trouble. But because I have a vertical asymptote between, I can easily make the lower one a max and the upper one a min. And this is exactly what the graph looks like. If you graph it out, you get something that looks very similar to this, which makes me super happy. So that's why I wanted to really start cluing in at the very beginning. Are there any vertical asymptotes with the function, the original function? Because if you have vertical asymptotes, you can sometimes have very confusing values like we did here. And if I had not had that vertical asymptote right here, there's no way I could have made this one a max and this one a min, because it would have been some sort of continuous thing, and that would just be it's an impossible creature to draw without the vertical asymptote. Alrighty, so that was step 5, sketching the graph, and we are done with the homework and ready to move on to the next section. So this is going to be a little bit of a long one, but that's okay. I will start the actual lecture right after I clear this. Clear. Okay, so now we get to jump into 3.4, which is concavity. So we're going to start off with kind of a little bit of a review. let's say that we have f of x, some f of x, and so that's the function. And then we start talking about f prime of x. So f prime of x, what is that? Well, it's the slope, right? But another way to say that is f prime of x gives us the rate of change of the function. Okay? Which is also our f of x. Gives us the rate of change of f of x. Well, what is another word for f of x? Y. So it gives us the rate of change of the y values. Also look at it that way, and that is totally not surprising because what is the definition of slope to begin with? Well, it's rise over run, which is the change in y over the change in x. Okay, I get for a small change in x or large, doesn't matter, but for a change in x, how much does y change is usually the way we think about it. Okay, and we always head in that direction, and so the change in y is up, it's a positive slope, change in y is down, it's a negative slope. Okay, another way to write that would be f prime of x greater than 0. What does that mean? Well, that means that it's going to be very strange. The y values are getting, here we go, bear with me, A, more positive, B, more, I did not put that, race, so more positive or less negative. What on earth am I talking about here? Well, if I look at a graph it like this, and I'll draw two lines. Maybe this one is going up a little bit more shallowly, doesn't matter. So as I move in this direction in the x, how is my y changing? Well, if it is a positive slope, my y values are getting more positive. Maybe this is 2, 3, 4, 5. They're getting more positive, right? Or they're getting less negative. Maybe this is -3 and this is -2. So I know it's a very strange way to think about it. What slope is really doing is telling you how the y's are changing as I move in that direction, in this direction over here, for the x's to the right. They're either getting more positive or less negative. Okay, now I can also say, let me clear this, that f prime of x is less than 0 means that we're getting the y values we are getting A more negative or B less positive. Okay, and if I draw a little graph over here again, I can see that same behavior. Maybe this one is shallow and this one is super steep, doesn't really matter. But as I head in this direction, maybe the values are going from -1 to -2 to -3, more negative. If I'm looking at the one above, maybe I'm going a little bit less. The y value is a little bit less positive, so maybe the y value is +4. And next thing you know, it's at +3, and then it would continue down +2. So this is an example of it getting less positive. Okay, so a positive slope, I want to rewrite this as a thing. positive slope equals more positive / less negative, and a negative slope equals, I don't know why I put that 1 there, it doesn't really belong. Get away 1, you never existed. A negative slope means I'm getting more negative or less positive. And what is getting all these changes? They are the y values, which is what my function is. F prime of x measures the rate of change of my original function. And another way to say that is f prime of x is measuring the rate of change of the y values, how the y values are changing. So it's a good way to say that. Okay, now I'm going to clear this. That was all lead into what we're doing next. So here comes the $10 question. What does f double prime of x give us? Well, f prime of x was the rate of change of the function. F double prime of x is going to be what? The rate of change of f prime of x, which is the slope. So f double prime tells us the rate of change of the actual slope, the f prime of x. Double prime, rate of change, single prime. Okay? So what on earth does that mean? Well, we're going to break it up like we did with the y values. If I have f double prime of x greater than 0, so it is a positive value, that means that the slope is getting, well, more positive or less negative. What on earth does that look like? Well, more positive means I'm going from a shallow slope to a very strong slope. So it's getting, this might have a slope of maybe at 1/2, 1, 2, 7, something like that. So f double prime of x greater than 0 means that the slope is getting more positive, or it looks like this, or less negative, which means that I'm going to be starting off with a very steep negative slope, but then it gets less steep. So it starts off steep and then gets less steep over time. Okay? Now, what about f double prime of x less than 0? Well, that means that the slope is getting, just like what we talked about earlier. In this case, the slope is getting more negative or less positive. What does that look like on the graph? Well, more negative is going down at a shallow angle, but it's now getting steeper and steeper, so it looks something like this. Less positive means it's going to be a steep positive value that is then getting more and more shallow, so it is starting out very steep and then becoming more shallow. Okay? So if I take these two right here and put them together, so f double prime of x greater than 0, we'll put these together. If you will, I'm going to make this the first one that I put together and this the second piece. So I'm going to start off going down like that. Then I'm going to add this piece to it and then go up like that. Okay, and this is what is called concave up. This is the full package of what you can see when you have f double prime of x greater than 0. You have something that's getting less negative, the slope is getting less negative or more positive, concave up. And we can also say that this is called a bowl shape. Okay, well, it looks like a bowl when you put them together. Now, if I do f double prime of x less than 0, what does that look like? Well, I'm going to start off with this is number 1 and this is number 2. So I'm going to start off and go less negative. I'm sorry, less positive right there, and then more negative right there. So this is called concave down, and it is an umbrella shape. Okay, so these are the ways that we can look at f double primes. When f double prime is greater than 0, I have one of two things happening. Either it's getting less negative or more positive, or f double prime is less than 0, it's going to be getting less positive, more negative. Ooh, that's hard to say. Gosh, and keep all that straight. But if you want a quick way to think of it, f double prime greater than 0 is what's called concave up. Concave up is a bowl shape. It means that the curvature is opening up. F double prime less than 0 has the curvature opening downward. That's called concave down, and it is the umbrella shape. And so this is burn these two lines right into your brain, because we are used to thinking of positive and negative slope. We've been thinking about positive and negative slope for years and years and years and years, ever since algebra. The very first algebra class you took back in, I don't even know where algebra is taught anymore. I think middle school, maybe, something like that. We've been dealing with slope, but what we haven't been dealing with is the rate of change for the slope itself. That is weird to think about, but this is absolutely critical to what we're going to be doing from here on when we're graphing these things. So we're going to have f double prime of x greater than 0 means the slope is getting less negative or more positive, which gives it this opening up shape, this curvature that is opening up. That is called concave up. I can't draw it because I'm not an artist, but you can picture a hand cupping upward like it is a bowl shape. F double prime less than 0 is going to be going less positive or more negative, and that is going to have curvature that is opening down, which is concave down or the umbrella shape. Okay? And that is all there is to this. So what I'm going to do is leave you with this. This is going to be the very first lecture right here. The whole thing can be summed up in this one box. Stare at it. Come back to it 2 or 3, 4 times. I'm not going to give you homework with this section because we've already gone a little bit long. And if I go through the example problems and give you homework, we'll go way over. This is where we like to stop in normal on-ground classes anyway. So just think deeply about this, become friends with it, and once you become super good friends with it, then you can, after you become friends with it, then you can connect this and make a cowboy if you want to. Sorry, this is This is what was shown to me the very first time that someone talked about concavity, and it stuck with me for the. I don't even know how long it's been since I first saw this, but making the cowboy just always makes me happy. So, concave up are his arms opening up, and then he's got bowed legs that are concave down. So, think about this, and then we will do the next lecture. All right. Take care. I will see you soon. Stay safe. Bye bye.